Welcome to UGC's ePathshala lecture series on computer science. The subject is on Introduction to Visualization. In today's module, we are going to look at abstractions in visualization. So the learning objectives for today's module are, it will introduce the types of various abstractions. We will also learn how the abstractions are being applied to the visualization. We learn about the design principles of abstraction and the various layers of abstractions, and we will also come to know about certain examples of abstractions in visualization. So what is this abstraction? Abstraction is actually the process of hiding details while maintaining the essential characteristics as it is. There are various types of abstractions that are possible in real world scenario. These types are classified as graphical abstraction types, layout abstraction types, event abstraction types, and data abstraction types. So let us see what graphical abstractions are. Graphical abstractions, they usually allow us to draw a line, fill a shape, or rotate a drawing, and are essential part of programming interactive visualizations. A new declarative approach to resolution independent 2D graphics that generalizes and simplifies the functionality of traditional framework while preserving their efficiency is a graphics abstraction. It is also a framework which makes it easier to produce high image quality and makes non-affine transformations more efficient. As a real-world example of graphical abstraction, we can talk about the implementation of focus context lenses, which gives higher image quality and better performance. So a graphical abstract should be an one image file and should visualize one process or make one point clear. For ease of browsing, the graphical abstract should have a clear start and end, and preferably reading from top to bottom or left to right. We can try to reduce the distracting and cluttering elements as much as possible. Here is an example for graphical abstraction, wherein we can see the entire image is given as one image file, and it is possible to visualize one process that is made very clear using this image. Next one is the layout abstraction. In layout abstraction, interactive visualizations often use these abstractions that produce some kind of layout, such as force-directed graph layout or a tree map. When laying out trees in a node-link diagram, a classical algorithm exists which produces the layout in linear time, but the resulting layout takes more space than it is necessary. So in this case, layout abstractions are necessary, and these present a novel algorithm that also runs in linear time but produces more compact drawings. Next is the event abstraction. Interactive visualization needs to deal with events such as mouse clicks and touch commands. Dealing with such kind of events is traditionally done either with blocking the input-output or using the callbacks. The former requires concurrency to compose the reactive paths, which also leads to non-determinism, while the later leads to inversion of control, wherein the control flow of the program is dictated by the events that occur and not by the programmer, which is also called as the event abstraction. Next comes the data abstractions. Data abstraction techniques are widely used in multi-resolution visualization systems, which try to reduce the visual clutter and facilitate analysis from overview to detail. The analysts are usually unaware of how well the abstracted data represent the original dataset, which can impact the reliability of results gleaned from the abstractions. There are three types of data abstraction quality measures. For computing, the degree to which the abstraction conveys the original dataset. The three different types of data abstraction quality measures are the histogram difference measure, the nearest neighbor measure, and the statistical measure. So these are the various data abstraction layers. So here in this figure, we can also see that the data transfer, next to the data transformation stage, we have the abstraction stage, and next to the visualization transformation stage, we have the visual abstraction layers. These two layers help in hiding certain cluttered information and helps in creating a very practical as well as clear image, which is shown as an output or as a visual to the end user. Multi-scale visualization. In the case of multi-scale visualization, visual representation changes as the user pans and zooms the surface. It is possible for us to get overview as well as lots of data which is highly abstracted in nature. It is possible for the end user to zoom into, and thereby the data density increases, which gives a detailed information. There are two abstractions that are possible in multi-scale visualization. One is a visual abstraction, wherein the entire visual is represented in different formats, but it is the same data set which is supposed to produce the entire visual. The next one is a data abstraction, wherein the transformations are applied to reduce the entire data set as such. In existing multi-scale visualization, some of the examples are cartography. PAT++ is a tool which helps in creating multi-scale visualization. Data Splash, XMDB toolkit is there, Advisor is there. The main limitations of all these toolkits are there is only one zoom pathway, and primarily visual abstraction is being applied on all these multi-scale visualizations. In multi-scale visualization, both the visual and the data abstractions are being used using generalized mechanisms. For data abstraction, they use data cubes, and for visual abstraction, they use a term called Polaris. So here we specify the multi-scale visualization using a graph of Polaris specification, which is also called as a zoom graph. So in the case of a Polaris is an user interface for exploration as well as analysis of data warehouses. It is also a formal language for specifying the queries and visualization, and it acts as an interpreter for compiling the specification into queries and for drawing the commands. In Polaris formalization, we can see that the visualization that is being described is described using the visual specification, which define the table configuration, the type of graphic in each pane, encoding of data's visual properties, and data transformations and queries. Each specification corresponds to a projection of the data cube. So this is a graphical example of the Polaris visualization. So this is a thematic map, and underneath this we can see the graphical notation of this thematic map, wherein the query is being given in a graphical format. So if you look at these three thematic maps, we can see the detail gets increased as and when we move from the top to the bottom pane. So in the top pane, we can see the entire map, and the query for the map is given in the form of a graphical format. In the next pane, we can see that all the states and their subdivisions are being provided by using a visual query, and similarly in the third pane we can see that the names of the states as well as the countries, everything are being produced using a visual query. So these are the three stages the thematic map produces. Next example for visual abstraction. To visualize the respective related tags, there are two algorithms that seem the most effective algorithm, which are called as the Fruchterman-Ringgold force-based algorithm and the Harel-Coran fast multiscale algorithm. For related tags network, both include the default vertex labels. The following, which is a social related tag network, was laid out using the Harel-Coran fast multiscale layout algorithm, and the view is as shown below. So in this case, it is not visually clear, and the most visually clear way to access this data is to partition the data into groups. The partitioning may be set up in the graph options area with the direction to lay out the groups in their own boxes, which are called as packed rectangles. To make the visualization more understandable, it may help to scale the visualization in the graph pane so that the images and the text labels may be easily read and there is no or less overlap. There is a clear visual that is being represented to the end user. Abstractions using programming languages. Different programming languages provide different types of abstraction depending on the intended applications for the language. For example, in object-oriented programming languages such as C++, Object Pascal or Java, the concept of abstraction has itself become a declarative statement using the keywords virtual or abstract and interface. Functional programming languages commonly exhibit abstraction related to functions such as lambda abstraction, higher order functions, bracket abstraction, etc. Programming languages also offer control abstraction as one of the main purpose of the use. Computer machines understand operations at the very low level, such as moving some bits from one location of the memory to another location and producing the sum of two sequences of bits. Programming languages allow this to be done at the higher level. Various object-oriented programming languages offer similar facilities for abstraction, all to support a general strategy of polymorphism in object-oriented programming, which include the substitution of one type for another in the same or similar role. Although as a generally supported rule, a configuration or image or package may predetermine a great many of these bindings at compile time, link time or load time, and this would leave only a minimum of such bindings to change at runtime. So these are the abstractions that are applicable in the programming languages. The next one is the abstraction at database level. The major purpose of database system is to provide the user with an abstract view of the system. The system hides certain details of how the data is being stored and created and maintained. The complexity should be hidden from the database users. There are several levels of abstraction in this case: physical level of abstraction, conceptual level of abstraction, and view level of abstraction. At the physical level, here we need to look at how the data is being stored. Example, whether it is stored in an indexed format or hashing mechanism, or it is stored in the form of a B tree. It is the lowest level of abstraction, and complex low-level structures are described in detail here. At the conceptual level of abstraction, which is the next higher level of abstraction, this describes what data are being stored. It also describes the relationships among the data. It is at the database administrator level. The next level of abstraction is the view level of abstraction, which is the highest level. Here, this describes the part of the database for a particular group of users. Can be many different views of a database. Example, tellers in a bank get a view of customer accounts but not of the payroll data. There are various data models. The data models are a collection of conceptual tools for describing the data, data relationships, data semantics, and data constraints. There are three different types of groups which are classified as object-based logical models, record-based logical models, and physical data models. In object-based logical model, they describe the data at the conceptual as well as the view level, and they provide fairly flexible structuring capabilities. They allow one to specify the data constraints explicitly in the entity relationship model, object-oriented model, binary model, semantic data model, info-logical model, and functional data model. In record-based logical model, an entity is a distinguishable object that exists. Each entity has associated with it a set of attributes describing it. Example, number and balance for an account entity. A relationship is an association among several entities. Example, a customer account relationship associates a customer with each account he or she has. The set of all entities or relationships of the same type is called the entity set or the relationship set. Another essential element of the ER diagram is the mapping cardinalities, which express the number of entities to which another entity can be associated via a relationship set. This is an example ER model. This is the overall logical structure of a database and can be expressed graphically by an ER diagram. Rectangles represent entity sets, ellipses represents the attributes, diamonds represent the relationship among the entity sets, and links are created where link are used for creating link between attributes to entity sets and entity sets to relationships. An object contains values stored in instance variable within an object. Unlike the record-oriented models, these values are themselves objects. These objects also contain objects to an arbitrarily deep level of nesting. An object also contains bodies of code that operate on the object. These bodies of code are also called as methods. Objects that contain the same type of values and the same methods are grouped into classes. A class may be viewed as a type definition for objects. The analogy is the programming language concept of an abstract data type. The only way in which one object can access the data of another object is by invoking the method of that other object. This is also called sending a message to the object. Internal parts of the object or the instance variables on the method codes are not visible externally to the end users. The result is two levels of data abstraction in this case. The data and relationship are represented by a collection of tables, and each table has a number of columns with unique names, example customer and account. In record-based logical models, record-based models do not include a mechanism for direct representation of code in the database. Separate languages associated with the model are used to express database queries and updates. The three most widely accepted models are the relational model, network model, and the hierarchical model. Physical data models. The physical data models are used to describe data at the lowest level. There are very few models, examples of unifying models and frame memory. These are some of the benefits of data abstraction. By data abstraction, we mean to gain something. That is, first, the interface protects the implementer from incorrect use of the data structure by the client. An interface also creates an abstraction barrier that protects the implementation. A client that uses the knowledge of the implementation not contained in the interface is violating the abstraction barrier. Second, when something goes wrong in the program, the presence of an interface makes it easier to assign blame to either the client or the implementer. Either the client is using the interface incorrectly, possibly violating the abstraction barrier, or the implementer is implementing it in an incorrect manner. A clear interface makes it possible to argue that one of the two needs to fix with their code. The third benefit of abstraction is the interface also gives the implementer the flexibility to change the implementation as long as the client is only using the implementation through the defined operation, and those operations are still provided by the new implementation. This flexibility results in a loosely coupled system, and the interface creates a contract between the client and implementer which frees them up to work more independently as long as they stick to the contract. Whereas in a tightly coupled system, the client and the implementation are not as free to change because changes to either are more likely to change the interface. So these are certain benefits of abstraction basically. So if we look at these benefits, it is understood that in these kind of data abstraction, the abstract layer will help the end user not to interact with the bare physical layer or the data layer, and it is not possible for the client to change any of the data that exists at the physical level. By way of these kind of abstractions, it allows only the implementer to just go and make any changes with respect to the data, and it doesn't allow the client to go and meddle up with the data. So these are certain benefits of data abstraction as such. Next one is a procedural abstraction. These kind of procedural abstraction provides mechanism for abstracting well-defined procedures or operations as entities. The implementation of the procedure requires a number of steps to be performed. A simple example is a debit operation which performs various steps to debit certain amount from the bank account. Hence, at the banking level, credit and debit become well-defined procedural abstractions. Procedural abstractions are used extensively by requirement analysts as well as designers and by programmers. Procedural abstractions are normally characterized in a programming language as a function or a subfunction or procedure abstraction. The temporal abstraction task. There is another one abstraction task related with respect to time which is called as a temporal abstraction task. These are time-stamped clinical data and relevant events. We use interval-based abstraction in these cases. It identifies the past and the present trends and states. It supports decisions based on temporal patterns, such as it helps in the modification of therapy. If the patient has a second episode of grade 2 bone marrow toxicity, which can last more than three weeks, it focuses on interpretation rather than forecasting. So these are certain examples of temporal abstraction task which helps in visualizing the time-stamped clinical data with respect to past state and trends and the present states and trends, and these two can be compared and the decisions can be made based on the past as well as the present trends and states. The uses of these kind of temporal abstractions are the therapy, it helps in therapy planning and monitoring. That is, example is to support the guideline based carrying mechanism. It creates high level summaries of time oriented medical records. It also supports modules for a medical decision support system. And visualization and exploration of time oriented clinical data is also possible with the help of temporal abstractions. So in temporal abstraction, we mean to say that it is time based, where it is possible for the end user to view either the past or the present data set, or at the same time compare the past as well as the present data set and come up with certain decision making methods or mechanisms. So till now we have been looking at various how abstractions can be created in visualization. So now let us have a look at the various examples of abstractions and visualizations. So this is called as a Twitterscape. This Twitterscape generates abstracted images of tweets that are being tweeted using the tweets and as well as the public user profile information that is available. These look like certain images, and the images are generated by replacing each character of each tweet with a pixel which is similar to that of an monospace font, and a color is being selected from the tweeter's online profile. These Twitterscape images, they try to abstractly represent a moment in time for a Twitter user, permanizing the tweets that the user would be reading and creating a snapshot of the moment through the colorful ways that their chosen community chooses to sound off. So have a look at this Twitterscape, which looks in the form of an image. The next example for visualization abstraction is shown here. Here there is an example of two display lists. By zooming outwards, the red display list, it becomes more reduced and abstracted when compared to that of the green display list, which has more details when compared to the red display list. The next example is the example that is being shown here. This is in the form of a tree. We can see that in the left hand side we have a tree of about 7 number of nodes. In that, if you look at node A, from node A we have node B, C and D as children to node A, whereas in the right hand side image we can see that the node A has been abstracted. So this is also a clear example of abstraction that happens in visualization. So if we click that node A, automatically node A expands to create nodes B, C and D, and once again if we click it, we can see that node A gets collapsed. So this is another example of abstraction and visualization. This is a visualization for the person's activity data set. So if we look at this visualization, this figure A shows the conventional scatter plot which suffers from severe drawback, wherein it is not possible for the end user to infer anything out of it. Whereas in figure B, we can see that the scatter plot gets converted into splatter plots which tries to synthesize new colors. The data points that are present in the sparse regions are explicitly highlighted. And then in figure C, we can see that the splatter plots with additional noise that can enhance the distinguishability in the dense regions. And in figure D, we can see that the number of data points before and after abstraction in this region which are being listed in the right hand side of it. So this gives a clear example of abstraction and visualization. The next example is an example of a molecule. Here if you look at this figure A, we can see that the focus is placed on the secondary structure of a chain while showing the back part of the molecule as a context. So this is a context part and this is a front part which is being shown in an abstracted format. Figure B shows the same molecule, but here we can see that there are three structural abstraction levels. The first one is a ball and the stick level, the second one is a ribbon level that is shown here, and the third one is a Licorley level. So there are three levels of abstraction that are shown in figure B. Now this figure C and D, they try to demonstrate how illustrativeness can be used to guide the attention. So we can see clearly that there is a distinction between the left hand side and right hand side part of the molecule, wherein here we see the left hand side we see an abstracted image, whereas in the right hand side we have a detailed image. So let us summarize what we have learnt in today's modules. In today's module, we have learnt about the various types of abstraction, namely the graphical abstractions, layout based abstraction, event abstraction, data abstraction. We have also looked at various abstraction layers, and the figure was also shown already. We have also looked at various examples of abstractions that are applicable in visualization. We have also looked at various examples of abstractions which are applicable in programming language also. Thank you.